In this video, we're again discussing applications of functions, and we're taking a sidestep here with this particular example and talking more about a concept or some vocabulary that you may encounter in this class. Questions like A through F here look a little bit different at first, and what's interesting about them, well, there's two things. Number one, these are the combination of functions. And that's interesting, this notion of combining functions together. But secondly, we don't have a formula for either function. Instead, in order to get a function result, we're simply looking at the graphs. And so I thought this was a good set of questions to ask, just to make sure that we're all on the same page with regards to executing these functions. So with part A, we're being asked to add f plus g parentheses 2. And I get a lot of students that think that this means f plus g times 2, and that's not it at all. Remember, with function notation, especially if I had a single expression, f of 2, you would understand that that means to evaluate the function f at the number 2. And if I had g at 2 or of 2, that would mean to evaluate the function g at 2. Well, as it turns out, this notation is expressing exactly this. Evaluate f at 2 and g at 2, and then sum them together. That's what's happening here. F plus g, both the function f and the function g evaluated at 2, and the results should be added together. So, since the function f is this red function here, we're going to look at the x value of 2 and try to peek at it. And it looks like when x is 2 on the red graph, the y result is 2 as well. So f of 2 is equal to 2. G of 2, again, we're looking at 2 on the x-axis. This time we're focusing on the y component of the blue graph, which happens to be 1. We have 2 plus 1. And 2 plus 1 is equal to 3. Part B asks us to evaluate f plus g at 4. So I'd like for you to try this one on your own. Please pause the video now and resume playback in a moment to check your work. Since f of 4 is equal to 1 and g of 4 is equal to negative 3, we would add 1 with negative 3 to obtain negative 2. Again, the y result of the f function plus the y result of our g function. 1 plus negative 3 is negative 2. The remaining questions in this group can be executed much the same way. F subtract g at 6, g subtract f at 6. You'll notice that these two are written in a different order, and you might be able to guess what's going to happen when we subtract in different orders. For part E and part F, we will multiply the functions together. Note in part E, this is not the same as f composed with g, if you've seen that notation before. This means something completely different when we use an open circle to combine two functions. That's called a composition of functions, which you may have seen before. We will revisit at a later time. But again, for part E, we're simply multiplying the two. So I would recommend that you try these on your own. Please pause the video and resume playback in a moment to check your work. And I think these are pretty fair solutions for C, D, E, and F. In the interest of time, I think we'll skip a few sections of the notes that I've posted online, although I feel that you should practice this set of questions on your own and see me for help as you need it. I'm going to jump down to example number 7 here, where we talk about the average rate of change. In one of the prior videos, we spent some time talking about the difference quotient and the instantaneous rate of change, but let's not skip over this fact that we can use the slope of secant lines to determine the average rate of change. This blue curve is the graph y equals 3x squared, or is at least a portion of it. it would also continue on the left-hand side of the screen as well. And there are three average rates of change that we would like to establish. We would like to know what the average rate of change of this function is from 1 to 3, from 1 to 5, and from 1 to 7. And they're essentially indicated here with the red secant lines. If we are going to evaluate the average rate of change from 1 to 3, what we're talking about is on the x-axis from 1 to the x value of 3. And so we're talking about the two coordinates here and here. We're not talking about the specific location of this guy, 1, 3. That just happens to be a coincidence that they're the same number. But instead, what we're worried about is the slope of this red line, this secant line. If I were to extend that, we would see that, that this graph, this red line touches the graph in two spots locally here. So we'd like to know what the steepness of that line is. Now, for those of you that are astute, you can see that the solutions have been presented to us already. I forgot to white those out in the notes, but that's okay. Let's see how we can establish those on our own. Well, let's recall that the slope of a secant line is simply equal to the slope function, y2 minus y1 over x2 minus x1. You might also see this written as delta y divided by delta x. Or with function notation, you might see something like this. The function evaluated at some value a minus the function evaluated at some value b divided by a minus b, or some other form of that. But they all mean the same thing. Let's take our two y coordinates and subtract them. Let's take our two x values, x coordinates, and subtract them, and simplify the fraction. So in this particular case, we could rely on the data points that have been provided. And we could say that our y values are 27 and 3, while our x values are 3 and 1. And 27 minus 3 is 24. 3 minus 1 is 2. And 24 divided by 2 is 12. So our average rate of change is indeed 12. If the coordinates, however, are not provided, but we have the equation to work with, we can still determine the average rate of change with just a little bit of algebra to show. So in part B, let's assume that that's the case. We need to find the slope of the secant line, which is the average rate of change. And I'll use this notation here, f of a minus f of b divided by a minus b. Now, order doesn't really matter when we're using coordinates, as long as we use the same order in the numerator and the denominator. If we choose a first, then b in the numerator, then we should use a, then b in that order in the denominator. So I'm going to use a being 1, and in this case I'll use b to be 5. So a equals 1, b equals 5, and these are our two x coordinates along the x-axis. So in the denominator I'll take 1 and subtract 5. In the numerator I need to find f of 1, and I need to find f of 5, and that's pretty easy to do since we have a formula. 3 times 1 squared minus 3 times 5 squared divided by 1 minus 5 will give us our slope of the secant line. You'll notice that when we subtracted in this order, we ended up with a negative 72 divided by a negative 4, which is good news because the solution ends up being a positive 18. And as our chart indicated, the average rate of change should have been positive 18. Now here again, average rate of change does mean slope. So the slope of this line and this line are 18 and 12 respectively. And the line may not look like it has a steepness or a slope of 18 or 12, but if you take a look at the scales and you see how the x-axis and the y-axis are scaled differently, hopefully that helps you understand that we are dealing with relatively steep lines here. Part C is completed in much the same way. The slope of the secant line is equal to f of a. And I'll actually just make the substitutions now. If we're going to look at the average rate of change between 1 and 7, we'll use f of 1 minus f of 7 divided by 1 minus 7. And what I'd like to show you here is how we can use our calculator, again, to solve this and make life a little bit easier. If I switch screens to the TI calculator, here I have a document open, and most of the time I tell you to press the on button, create a new document. We ignore the option to save. And normally I have you open up a calculator page, but this time I'm going to have you open up a graphs page. In the graphs page, I'd like to store the function that we were given just a moment ago, 3x squared, and press enter. There's a shape of the graph that we saw on the notes page, but I'm not actually going to use the graph to answer the question that we're faced with right now. What I'm going to do is I'm going to create a calculator page, and I'll show you how we can evaluate this expression pretty easily now. So I'm going to press Control and Document. Control and then the document key will actually add another page to our document. This time I do want to work with a calculator. On this page, I'd like to create the empty fraction, just like we had a minute ago. And on our notes, we needed to evaluate f of 1 minus f of 7 over 1 minus 7. So I'm going to try to recreate this in the calculator. Well, to evaluate the function at 1 and to evaluate the function at 7, this is pretty easy to do. This button here, the variable key, stores all the variables or holds all the variables that are associated with this document. And right now the function is acting as a variable because it can take on any value based on what x we provide. So I press the variable key, and normally there's a list of variables that we can choose from. This time around I only have one variable stored in the calculator. So I'll click on that, or I could press the enter key, and it will select that variable, that function, f1. We're going to evaluate that function at the number 1 and move to the outside of that parentheses, and we'll subtract another function, this time evaluated at 7. So I'll press the variable key again, select function number 1, that's where our equation was stored, and this time we'll evaluate it at number 7. I press the down arrow to jump to the denominator, and we'll subtract 1 minus 7 and press enter. And now I have f evaluated at 1 minus f evaluated at 7 divided by 1 minus 7, and we can see our average rate of change being 24. So hopefully you can see the benefit to using that calculator. If we had many calculations to perform, we'd be able to perform those relatively quickly. For example, what if I started choosing a bunch of x values that were getting closer and closer to the a value of 1? Well, in the calculator I can repeat that pretty quickly. So we'll use an a value just slightly bigger than 1. We'll call that, say, 1.5. Oops. Minus 1.5. And so the average rate of change between 1 and 1.5 is 7.5. Well, what if I wanted to get a little bit closer? What if I wanted to find the average rate of change between 1 and 1.1? Well, I can do that too. There's our average rate of change. What if I wanted to get even closer still, between 1 and 1.01? Well, again, we can perform that as well. And all of those average rates of change were calculated very quickly by having that function stored in our calculator. And we're also starting to see a pattern in the numbers that we've selected so far. We're starting to see a pattern in the average rates of change. For future reference, this is a calculus concept. The patterns we discover in our average rate of change calculations lead us to estimate or determine what our instantaneous rate of change will be. I hope you found this video helpful. If you have further questions, please make sure that you reach out to me and I'll respond as quickly as I can. Thanks for watching.